this is a suggestion from completely outside the field. I probably should have written a wild suggestion from outside the field, because our interest is in algebras of concurrent distributed systems, nothing to do with quantum mechanics. But lately we are interested in probabilistic concurrent systems, and it just seemed to me the algebra was very similar for quantum, the possibility of an algebra for quantum. So we're proposing an algebra which gives meaning to a diagram of this form, in which the objects, the squares are have state and transitions. Okay, it's not an algebra of the flow of data, but an algebra of objects, in which some of the objects are classical, Alice and Bob, and others are, we'll see, some of them are a bit quantum entities. Okay, the quantum entities are these 3 qubits. It's not a diagram of flow of data. The reason we think it's a good idea to have such an algebra is the following diagram, which is a diagram of the same kind. It's a classical diagram. It's clear, in order to describe this, you have to have an algebra. You can't describe the state space of this thing in one globally. You have to know the parts and how to put them together. So this is a classical expression in an algebra. It's an algebra and a classical algebra. Here is an example with a classical object and a quantum object. So the algebra, is analogous to these sequences of algebras here. Matrices, relations. These are the arrows in the categories. Relations, bimodules, spans. The composition always looks a bit the same, sum of products. Okay, or co-end of tenses and so on. The last one is the one that we're interested in really, span, except we're more precisely interested in span of graphs. The span of graphs, span doesn't mean the same as has been used in other lectures. I don't mean linear span, span is a pair of arrows. Span between 2 objects is a pair of arrows. This means that you have internal state in the object, in the arrow. So the actual algebra is an analogue of the category of spans of graphs. And in this case, a graph itself, the span of graphs, may be thought of as a matrix. Sorry, a graph itself is a square matrix, okay, whose columns and rows are the states of the graph, the vertices of the graph, and the entries are sets of arrows between the vertices. So a span of graph is a doubly indexed family, a matrix of whose entries are square matrices. All right. So there's 2 levels of matrices in this thing. So the idea anyway is to replace the square matrices here by linear operators. This is another algebra. Okay, unfortunately it's illegible. So what's illegible on my computer? Is it legible or not?
It's there, it's not.
I'm sorry, but so I read it to you. We have 2 alphabets, A and B. We have a vector space, and we have a family of an A-B index family of operators on this vector space B. That's what it is. That's all it is. The second part is what's the composition. I mean, the main operation is composition. The composition is that you take phi circle psi at AC is the sum of the tensor of the operators phi AB, psi BC. Okay? So that looks like a little bit like a matrix composition, but it's not because it's got a tensor. However, the matrix composition does come in because a behavior means, what's a behavior? It means a sequence of applications to a vector of the matrices. And that means you're using composition of matrices to produce the behaviors. Just like, for example, the stochastic matrix, you repeatedly apply the stochastic matrix to get a behavior. But here we have a family of matrices, and you're applying a family of matrices. Okay, so there are two matrix multiplications, composition of entities, and the behaviour comes out of the composition of the operators. So, what's it? Among these, by the way, this is much bigger than quantum automata, it's much bigger than finite state automata. It's a much bigger algebra. So it's an algebra much more extensive. Inside, there are ones which have unitary operators and projections, which you might call quantum automata. And there are other ones in which the state space is C to the x, where x is a set, and all the matrices are zeros and ones. Okay, so that you have, that's a classical automaton. Okay, we'll see the example in a minute. All right, but so there are two different types of automata in here. One which you could call quantum, the other you could call classical. I've just said this is much more general. I mean, that's why I say it's a wild suggestion. I'm not saying it's physically realisable, the whole thing. But it's necessary in order to produce a compositional theory to have these extra automata. So here's the thing that's been screwed up. Okay, so here's a particular qubit, a single qubit, which has state space C squared, and the left has a left alphabet and a right alphabet. Now the meaning, by the way, you should think is that one of these automatons has its own transitions, and the alphabets are the transitions on the border of the automaton. They're not input and output, they're the reflection on the border of the transitions of the physical system. So here are the in this particular case, it's a particular qubit which has various unitary matrices which occur when there's a signal on the left. Let me talk of signals, but they're not really physical things. There's a signal on the left which says Hadamard, and there's always this symbol of epsilon which means no signal, empty signal on the boundary. This is an identity unitary. The rest of it, this is part of a controlled NOT gate. Okay, with two of them together form a controlled NOT gate. But this is just part of it, but it's divided into two things which are not quantistic in their own. So, but you can draw a picture because you just draw the edges with the labels. I left out all the things that were zero. For the ones which had a number which was not 1, I put the number in. Okay? So this is a transition corresponding to a Hadamard matrix. These are transitions corresponding to a part of a controlled NOT gate. Okay. Here is Alice. By the way, this example is not intended to make it a nice picture of this particular protocol. In fact, I put a very complicated thing here. The reason is that the experience in concurrency theories, this is where one of the difficulties. There are two difficulties in concurrency. You have billions of components. But secondly, the components are not nice automata. And you have lots of them stuck together. You have no idea what's going to happen just because of the complexity of this finite state control. So this is Alice. Remember, Alice is just moving, and things are happening on the border. So the first thing is a C0 signal occurs on the right, then a Hadamard occurs on the right, then a measurement occurs, and then a signal. This one is a signal sent to on a classical channel to Bob. Okay, there are three channels. Two of them one is a classical channel. The other ones are just these idealized things which I don't know what physical meaning they have, but they enable you to produce composition. So the composed system is this. I didn't tell you what the tensor was, but there's also a tensor as well as the composition. The classical part, this part that I've written there is a classical automaton in the definition that I gave before. All the operators are measurements or unitary transformations. Then, if you look at the behaviour, starting from Alice in the first position and Bob in the first position, and an arbitrary value to the first qubit, and a Bell state in one of the, I don't know whether I've got all the things there. A Bell state in the other two qubits. This is a closed system, by the way. That's a closed system because there's no wires coming out. So it's a single matrix when you multiply. When you multiply or do the calculate, it's just a single matrix, and evolution is just repeatedly applying this matrix to this state. And by the way, an important point is that c to the x is a sum, and the distributive law is important, but I don't want to go into that. So you get a calculation. At the end of the calculation, the final state, by the way, I forgot to say, we're really just looking at non-deterministic aspects of quantum things, nothing to do with probability in this, just non-deterministic aspects. In any case, the third qubit has become the value of the first qubit. It's not quite clear to me in this picture what this state is at the end, because Alice is mixed up with the other two qubits. However, if we change Alice so that her measurements are actually observable, what does that mean? It means this is a classical channel here, and it has sense to talk about a diagonal on this channel. And if you can see this here, you don't just get one matrix. It's not a closed system. You get 5 matrices corresponding to the different signals that occur on this channel. So the behaviours are different because they're associated with observations on this wire. They could also be observed here. But the natural thing, in a way, is to look at the thing with a diagonal. If you do this open protocol, you get 5 possible states after 4 moves, which are all the different results of all the different measurements and the qubit value transferred, and Alice and Bob in final states. There is another possible result, that you get 0, because 0 corresponds to the fact that the thing doesn't occur, right? I mean, there are edges which have 0 on which don't occur. Okay, I think that's, sorry. Just two things. I mean, this classical channel just has Frobenius and separable algebra equations, being a classical channel. There's papers, it was actually 1987, the paper that you referred to. I mean, there has been, this is a wild suggestion because we are not involved in quantum mechanics, but these particular algebras I think are very interesting. Even the one that I just introduced, I think is a very interesting algebra, and we haven't done a large amount of work on these kind of algebras. The cat is still alive. Thank you.
Are there any questions, comments? So, the sort of thing you would expect is there is really some interaction of this algebra with the Frobenius structure of some kind.
By the way, the thing I described was just a concrete algebra.
Yeah.
And since it's just a preliminary thing, we haven't investigated it as an algebraic thing, right? It's very similar to the other algebras, but we haven't investigated.
You would expect some interaction of the two, like of your explicit Frobenius structure which you want to introduce. You would expect some interaction with your algebra there.
Well, but the actual equation is related to the. I mean, that's a component, right?
Yeah, yeah.
I mean, it's related. It's related to the tensor, that component. Is that what you mean, or you mean something different?
Yeah. I don't see the Frobenius structure coming out and doing any work. The sort of.
I agree that there's nothing in what I said uses any of the abstract algebra. Uses any of the abstract algebra because it's just a concrete algebra which we looked at recently and thought was interesting. Obviously, obviously the algebra should be used. The abstract algebra should be used. But further, we should be able to, if this was really worth following, we should be able to produce the algebra flow out of this one, right? I mean, if you have an algebra of this type, that was one of the remarks I made, which I deleted because the referees didn't like. But I mean, out of an algebra of objects, you can produce an algebra flow. Naturally, I mean, but I didn't explicitly describe it. Which would be related to the kind of diagrams that you did.
Right. Yeah, that's what you would like to see then. Yeah.
Okay.
Peter?
So what about,
Yes.
so we discussed compositionality, right?
Yes.
So when you have a sort of world of classical objects and a world of quantum objects, then somehow you expect them to live in a bigger world of physical objects, right? And that objects somehow compose. So yours also live in a bigger world, namely the world, where you have all the automata, but
Yes.
somehow neither, like, you can assemble a quantum automaton from parts that are not really anything physical, right? Is that, do I understand?
That's true. I mean, this
Is that a
algebra.
problem, or is that a bug or a feature?
That's a good question. It's a bug. According to me, it's a feature, but you may want to say it's a bug. A bit. So, I mean, it's not unusual in mathematics to have to introduce ideal entities in order to. I mean, the problem of compositionality is really important. Okay? It may not be in computing. I don't know if there were really quantum computers, it would become serious. The problem of compositionality. Okay, so I mean, if you draw small ones, compositionality doesn't really matter. You can describe the whole system. If you have a thing like the 4004, you have to make it out of parts and know how they're put together. If you can produce a different type of compositional theory, this was it's a very simple compositional theory. This algebra is the most simple you can imagine. It's just the sum of the tensor.
So many people in this room are concerned with sort of how you combine physical systems and what kind of laws they satisfy. Whereas probably what you're doing is more foundational in the sense that you can probably reason about systems. That's for you. So would that be it?
I don't know how to respond to that. It's a wild suggestion. Thank you.
Any more questions? Okay. Thanks.